Let's continue. Okay, now we are going to talk about one of the most confusing things in the formalism. Please ask questions, okay? And this is also important. In my opinion, this is one of the most useful things. If you are going to do this thing, it just comes around over and over again. So I want to talk about something called simultaneous observables. And it will be related to uncertainty principle. Maybe today, maybe next hour, but we will see. So the key is, so what we saw in the generalized statistical interpretation is that if you are measuring a Q, right, what you need to do is go to eigenbasis of Q and measure it. So if you are given an initial state, you need to expand it in the eigenbasis of Q. And now the question is, what if I want to do two different measurements? Suppose I want to have like two things, an operator A and an operator B, and of course there's no such thing as observing them simultaneously. In the lab you need to choose one, observe it, and you need to bring the other one and observe it. And the question is, can we observe two different observables simultaneously? And the result is if the commutation A comma B, so these are operators, is 0, A and B can be observed simultaneously. Okay? And why I want to spend as long time as it takes to make sure we understand this concept. Okay, this is important. Another way to say this, because in the measurement, right, what do? We find the eigenvalues and eigenfunctions. Another way to say this is like we diagonalize an operator, right? And if A and B can be observed simultaneously, or if A comma B commutation is 0, another way to say this is they can be diagonalized simultaneously. Or another way to say the same thing is they have the same eigenbasis. Okay? And if that's not the case, suppose this is not the case, A comma B is not equal to 0, then we cannot measure these two things. And we are going to call these incompatible observables. Good. So I want to prove these things in a couple of steps. So first, let's do the easy one. So this one, like easy warm-up. Suppose A and B have like a common complete eigenbasis. Given A and B have a complete and common eigenbasis. Then the question is, do they commute or not? So let's prove that. This one is easy. So if this is given, the meaning of this sentence is like I can take A and hit on a set of functions fi, and I can find some ai and fi, right? And I can do the same thing with b, but b is going to have its own eigenvalues, bi. And the question is, what is the commutator? And the commutator is ab minus ba, right? This is the commutator. And the way we calculate the commutator is we hit on functions, right? These are operators. We don't know what they do by themselves. We look at them by what they do on states. So this is psi. And because this is like a complete basis, I can expand this psi in this fi basis. So this is fi basis. So let's do that. So what I'll do is I'll take this. Let me open up some space. And I'll hit on n, let me call it I, some expansion coefficient ci and fi. Because I only know what a and b does in their own eigenbasis. Now let's carry this. So this is the sum. Now the operator will go like this and hit fi. So let's look at this piece by piece. A, B, fi. So B times fi, what is this? We just wrote this. Bi. And now Bi is a number. The thing we like about numbers is they just go around. And I take it outside. Now I hit with A, fi. What is this? This is the assumption. This is going to be Ai, Bi, fi. And similarly, I can do the same thing with B, A, fi. And this is going to be exactly the same thing. Ai, Bi, fi. And now I can plug this in here. So this is equal to sum over I, Ci, Ai, Bi minus Bi, Ai, Fi. But these are numbers. So AB is equal to BA for numbers. Therefore, this is 0. Then this is 0. Since this commutator AB minus BA is 0 for any, right, this is an arbitrary state. If it is 0 for any state, we immediately conclude A, B as an operator identity should be 0. Okay, they commute if they have common eigenbasis. So now, then they are compatible. Yes.
Shouldn't it be 0 cat, the result?
No, it's not 0 cat. It is 0 number. 0 cat is something else, right? We are going to see there's like a different, when you put it in this form, it has a meaning. 0 means 0, right?
But when we multiply 0 with fi, it doesn't give a number.
Right, take number 0 and multiply any state, it's going to give you 0. Right? 0 is such a thing, whatever you multiply it with, result is 0. But that's a good point. Like at some point there will be things like this. We need to be careful. Thank you. Good. So now, this is kindergarten stuff. Now let me just increase complexity just a little bit. So this is not as easy as this one, right? But it's a little bit more like a little harder. So suppose this is given. A, B is 0. Suppose this is given. Then the question is, do they have common eigenbasis? Or this is saying the same thing. can they be diagonalized simultaneously? So let's pick one, right? B itself is going to have an eigenbasis. Let me call this B times, and typically it's good to label the eigen states with eigenvalues, but for like not to have clutter, let me not do it for the moment. Let me write it and I can drop it in a little bit, something like this. So this is given, right? For any operator, if it's an observable, I can write this because they have real expectation values, and they can be diagonalized. They are Hermitian operators, and their eigenvalues are real. We know these things, and I can write this. But now I want to see if this F is also a good basis for A. So what I want to do is I want to hit with A from the left. So I take the same thing and I put A here. Because B is a number, right? Numbers just commute, so this is A. Good. Here is given to us A, B, commutator is 0, and that means AB is equal to BA. So this is given to us. Now I can use this information here, so this is going to be BA. Then if I rewrite this equation, here is what I get. So this is B A times FB is equal to B A times FB. Okay. We can pause here. This is important. If anybody feels lost, ask me. Everything you need to know is here. Good. But this equation is telling us, okay, from looking at this, if F is an eigenstate, then A times eigenstate of B, then A times F is also eigenstate. And you can see it is an eigenstate, right? So look at this blob and this blob. So it's eigenstate of B with the same eigenvalue. Good. Now I have to consider two cases. This is the one I called you easy one, and the difficult one I left it for the end. Now, case 1, assume non-degenerate spectrum. So that what this means is all eigenvalues are distinct, right? And they have their own eigenstates. If the spectrum is non-degenerate, and if this sentence is given to you, like F is, right, an eigenstate with eigenvalue B, A times F, right? If you hit an eigenstate with an operator, you get another eigenstate. But if it has exactly the same eigenvalue, what does it tell you? These are, yeah, I'm using the degeneracy, but like right now there is no degeneracy. We said there is no degeneracy. F is an eigenstate with eigenvalue B. A times F, let's call this some F tilde. If F and F tilde have the same eigenvalue, what do we know about F and F tilde?
They are the same ones.
Exactly, right? They are the same up to a constant. Because if there is a given state F, and if I multiply with alpha, it's also an eigenstate, right? Because things are defined up to a constant. From here, exactly like you said, we say A times F should be proportional to F, and proportionality constant, if you choose A, but you can see this is also an eigenvalue equation. Therefore, what we saw is if B times F is some B times, right? If there is like an eigenstate, the same state is also an eigenstate. If there is a commutation and if the spectrum is non-degenerate. And from here, typically, to avoid clutter, I didn't label, but proper way to do this is like this. You have A, you label the state with eigenvalues, and this tells you what to put here. This is A times FAB, and for B, FAB is equal to B times FAB. Good? Anybody feeling lost? We can rewind, and hopefully everybody understood that. The only thing we assumed so far is A and B commute. This is given to us.
The lowercase a and b.
There's no relation, it's arbitrary, right? A is an arbitrary observable with its own eigenfunctions and eigenvalues. A's are whatever they are, a set of A's, and B's are a set of B's. They are completely two independent observables. So what we said here is, so this, we start, right? We say that B has its own eigenvalue equation. And I hit on this equation with A. From here I found this. Then I say, if this thing is an eigenstate, this thing is also eigenstate. Because this entire equation is also an eigenvalue equation, right? I see here some blob and exactly the same blob, and B as an operator, B as an eigenvalue. From here I see that A times FB is an eigenstate with the same eigenvalue. But here is the critical point. If there is no degeneracy, that means, right, B can come out only if you are hitting on the same state. And here that's what we said. So if this is F tilde is equal to AF, and because of no degeneracy, it should be proportional to F. And that proportionality is another number. It's a completely different thing from B, little b and big B. It has nothing to do with that. But the thing is, it's a number. And as soon as we write this number, this is an eigenvalue equation, then that means we can write simultaneous eigenvalue equation for A and B.
So A is eigenvalue because AF, big AF.
Exactly. Yeah, exactly. Because we show this, big F is equal to, big A times F is equal to little a times F. This is an eigenvalue equation. This immediately tells us F is an eigenbasis for A. But since F was also an eigenbasis for B, from here we said that's what it is. If A and B commute, and if there is no degeneracy, they can be diagonalized simultaneously, or they can have simultaneous eigenbases, or they are compatible observables.
But they have the same basis.
Yes, now they have the same basis. This FAB is the same basis. Good. Now is the tricky one and the most difficult one, but I think if you got this, the next piece is just a technicality. So this case 1 was assume no degenerate spectrum. Case 2, suppose we have like a degenerate spectrum, and this is, let me note, so this is hardest thing we will do today. It's not hard, but I find it confusing, right? Confusing to understand, confusing to explain, because there are a lot of words. Hardest today. And I will show it only for, like, suppose like assume like there's like a twofold degeneracy, and any higher degeneracy is standard. Once you show it for twofold, it's valid for any higher case. Let's assume twofold degeneracy. So twofold degeneracy means the following. That means, so B can hit on F and gives you a B, F, and there can be another function B times G, which is also B. This is the meaning of twofold degeneracy. You can see, right, B and B, they have the same eigenvalue, but F and G are distinct states. So that's the meaning of degeneracy.
Can you explain again? I didn't understand.
So previously, like in that case, we said there is no degeneracy. Now I am saying, what if we had a degeneracy? What if this equation B here, this first equation we wrote, had a degeneracy? And the meaning of this is there can be not one function, but two functions, F and G, in case of twofold degeneracy. You hit with B on F, you get little b. You hit with B on G, and you get little b. Right? You are hitting on with the same operator, but on different functions, but they give the same eigenvalue. That's the definition of degeneracy. Now let's do what we did here. Like what did we do here? We wrote the eigenvalue equation for B and hit with A. Let's do the same thing. For example, this one. So let me hit with A. And I'm hitting on the entire equation like this. And this thing is going to give me A, B, F is equal to, so B is number, so A is going to jump over and bigger A times F. Good. What was given to us? A commutes with B. AB is always BA. So I can use it here. So this piece is BA. Now I have B A F is equal to B A F. You can see there's like a blob here and a blob here. 8, oh yes, so, yes, thank you. Like this, yes. Now, A times F, what can happen is the most general thing. It can have an F component and it can have a G component, right? And there can be some arbitrary coefficients. Let me call this U1 plus U2. And if you hit on this state with B, it is an eigenstate because this one is going to, okay, hit with B and C eigenvalue B, right? Is that clear? Maybe I can pause. Right? This is the most general thing. But the problem with this thing is we lost what we had previously. Previously we had A times F was a constant times F itself. Now you can see I'm not outside this constant, right? A different state came out here. And I can do exactly the same thing for the second degenerate state. So A times G is equal to, I don't know, this is U3F plus U4G. So it seems like F and G are eigenstates of A, but they don't seem to be eigenstates. F and G are eigenstates of B, but they don't seem to be eigenstates of A. And now is the hit. This is not a problem, right? This is not a problem because I can find a combination of F and G and make this combination an eigenstate of A. What I mean is we can find a new basis. So this is F tilde is equal to, I don't know, some V1 F plus V2G and another one G tilde where this is V3F plus V4G, and if I can choose V1, V2, V3, V4 in such a way that this can be an eigenstate of both A and B. Do you have a question?
We came up with F and G just because we already knew that BB has two measures.
Yes, yes.
If that was true, then we would have equal B, A, B, three different things.
Yes, yes. So we, like said, suppose there is a degeneracy, and for degeneracy we assume twofold degeneracy, then now this is given. All these assumptions means this is given. There are like two states, F and G, with the same eigenvalue for B. And when we hit on it with A, we saw F and G are not eigenstates from here. We see F and G are not eigenstates of A. And now we said this is not a problem. We can transform F and G to F tilde and G tilde. This one is trivial, right? B times F tilde. Because this is F and G and each one has the same eigenvalue, this is B times F tilde. Similarly, B times G tilde is again B times G tilde. And the last piece of the proof is we should show that we can choose V1, V2, V3 and V4 in such a way F tilde and G tilde are eigen states of A. Once we are once we do that, we are done, and that's the last piece. So right now, so anybody has any problem with this, right? So this F tilde and G tilde, this new basis, is an eigenstate, eigenstates of B. There is no problem with B, and eigenvalues are still B. But what we need to show is A times F tilde. I don't know, let me call this A1 times F tilde, and A times G tilde, let me call this A2 G tilde. We should show that this is doable. This is correct. If
Assuming the degeneracy of inverse for the B operator?
yes, I mean A1 and A2 can also be the same, but to make it more general, the most general thing is if they are different. If they are the same, there's no problem. The proof still works.
Okay.
So once we show this is possible, we are done. There's nothing else to prove, I promise. And that's the hardest thing, yes.
Are we assuming F and G is eigenstate and they are orthogonal, right? But
Yes, I am assuming they are orthogonal. Like there are like two orthogonal states, F and G, but the problem is not if they are orthogonal. The problem is they have the same eigenvalue under B. If you hit on F with B and if you hit on G with B, although they are orthogonal, they give the same eigenvalue.
okay, when we multiply bra F tilde in the first equation, we will get a number different from 1.
So this one,
No.
so this one,
Yeah.
you want to multiply this with bra F tilde?
Yeah. Shouldn't be. He has a not 1.
No, it should be one, but you know, like F tilde and F, right? You also need to, right? So there is like, this is F tilde F. You need to calculate this. And this is F tilde G. You need to calculate this, right? F tilde F, you can see where they have, right? that's perfectly fine. You are right. If this is 1, this side should also be 1. But I don't know if you think maybe you imply that this f tilde times f is 0 or something like that. Right?
I multiply with conjugate of f tilde.
Yes.
Right. But it will give v1 square plus v2 square, right?
No, you don't know what. Okay, you are writing right f tilde. I see. Yes, I think yes. If f and g are orthogonal, yes, they are going to give you v1 squared plus v2 squared, or more generally v1 like this, v1 squared plus v2 squared. Is that the question? That's correct. Yes. That's not necessarily 1, right? Or if you normalize, yes, this is 1, but there is still a degree of freedom inside v1 and v2. That's correct. You can call this 1, and that's perfectly fine. But I'm not going to assume that, because I don't need that. I want to keep it a little simpler, so I don't concern myself with normalization at the moment. Any questions? So last piece is I'm going to show this is possible, and we are done. And I'm going to generalize the message, and that will be the end of the day. Any questions? So what I propose is like, let's write this equation and see what it gives us, and let's write this equation and see what it gives us. So this is, let me write this. A as an operator acting on f tilde. And what is f tilde? F tilde is defined here. Let me take it. Should be equal to, and this is A1 times the same thing, f tilde. Let me open up some space. And what did we call? There is like here two terms. V1 is a number, A times F. Here, V2 is a number, A times G. But I defined what A times F is here, right? Here, A times F, I called it U1, something like that. So this is, so this thing is V1 times this entire thing. And similarly, V2, A times G is here. This is A times G. This is here. So this entire thing is left hand side. This entire thing is right hand side. You can see there is like F component here, F component here. There is like G component here, G component here. And at the end, what multiplies F and what multiplies ket F and what multiplies ket G should be identified. They should be equal. So let's write this and see what this equation means. For example, coefficient of F on the left hand side is, so this is V1 U1 plus, so I took this term, there is another V here, V2 U3, I take this one, should be equal to this one, A1 V1 plus, that's it. There's nothing else. And lastly, V1, what's that? I'm only looking at ket F. And I'm going to do the same thing with the ket G. Was that the question? Is that okay? Now this is V1 U2 plus, and there's another what am I doing? doing it. So V1 U1 plus V2 U3F. Okay, this is the coefficient of G. So this is G. So this is V1 U2 plus V2 U, which one? U4. Thank you. Is equal to the coefficient of G on this side is A1 V2. Now I want to rewrite this equation in a nicer form. This is you can see I can write this like U1, I think let me write and we can fix U1 U3 U2 U4 as a matrix multiplying V1 V2 V1 V2 is equal to A1. Okay, I think that's it. V1 V2. What is this equation? Right, eigenvalue equation, right? Then you can just find eigenvalues and eigenvectors of U1 U2 U3 U4, and this immediately tells you what V1 V2 to choose. And if you put that V1 V2, you can get an F tilde. And similarly, we can do exactly the same thing for the second eigenvalue. Like the second one is exactly the same, only this one changes. And this says, okay, then F tilde and G tilde can be constructed after finding eigenvalues and eigenvectors of this U object. Let me call this U. And once you do that, you are done. Now we have proved A and B can be diagonalized simultaneously if they have two-fold degeneracy. And for any fold degeneracy, you can do exactly this, only the size of this U matrix is going to be bigger, right? There will be some, okay, this is the jargon. There will be some degenerate manifold that A does this. Within this degenerate manifold, you can make a transformation to F tilde and G tilde, where this Neve basis is going to be eigenstate of both A and B. Good? Okay, the proof is harder, but at least I don't expect anybody to prove this, but I expect you to remember this. If A and B commute, they can be diagonalized simultaneously. That's it. I mean, you have seen the proof, you believe, but I expect you to use it. So this is abstract way of thinking. Let me generalize and give you, yes?
Is it matrix form of
Can you say one more time?
the matrix form of equation?
So this one.
Yes, in here we want to matrices algebraic. A1 is algebraic. What is the U1?
So there is like U1, U2, U3, U4. There is like a matrix, and this matrix is coming from this, right? From the action of A on your F and G function. Hit on F and G and find U1, U2, U3, U4, and put it in that matrix form. And if you diagonalize this new matrix, you construct F tilde and G tilde. Now, F tilde and G tilde are eigenstates of both A and B. Okay? So, I'm almost done. Hopefully, you will see how this is important and why this is relevant. So, this can be done for a set of observables.
John,
Uh-huh.
the matrix form
like in the second matrix, should there be V3, V4 or not? Like there's A2, that's why
I think yes, I think you're right. This is going to be like V3, yes, V4. This is going to be V3. You are absolutely right. Thank you. Yes. Let me check my notes. Yes, this is 3 and 4. Thank you. So this, what we did, can be done for a set of observables A, B, and C, dot, 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 right? And in that set, any two observable commutes with itself. Then we call this mutually compatible set. Any member of this set commutes with itself, then you can diagonalize all of these observables simultaneously. Okay, and if suppose you have like three members, like A commutes with B, and A commutes with C, and B commutes with C, they are all 0. That means you can have common state A. Now it's good to put labels of each eigenvalue. A, B, C, hitting on this is going to give you A, F, A, B, C, and the same thing for B and C. So if this is B, this is B, and this is C, this is C. So if this is given, we immediately can tell this is given. Because we did it for 2, we can do it for any other 2, and then we can do it for 3 sets. And here's the example. Maybe in a couple of weeks we are going to start talking about hydrogen atom. And there are like 3 operators that commute, they are mutually compatible. Hydrogen atom. There is like Hamiltonian H. There is going to be L squared, square of angular momentum, and there is going to be LZ. This is a mutually compatible set, and each one is going to have, for example, A is now H, B is now L squared, and C is LZ. And the eigenvalue of H is going to be labeled with N. Eigenvalue of L squared is going to be labeled with cursive L, and this one is going to be M. N is going to be the principal quantum number, L is going to be angular momentum number, and M is going to be so-called magnetic quantum number. Therefore, for this set, you are going to be able to write immediately an eigenstate like this. And this eigenstate is going to be eigenstate of both H, L squared, and LZ. Okay, and this will come from this proof. Okay, so next time I'm going to show if this is violated, if these two things do not commute, there will be like uncertainty between these two observables. We are going to calculate that uncertainty, and we are going to call these two operators incompatible observables. Good? Thank you.